Hello and welcome to another Data Scholar Code Along. This week we are going to review autoencoders. Now, what an autoencoder is, it's a type of artificial neural network and it's used to learn data codings in a generally unsupervised manner. The goal of an autoencoder is to learn a representation called an encoding for a set of data, typically for dimensionality reduction. And what we do is basically it sort of trains the network to ignore signal noise. Along with the encoding, the network also learns a decoding function to convert the encoding back into the original data space. They're typically composed of an encoder function that maps the input data to a lower dimensional representation, and the decoder function that maps the lower dimensional representation back into the original data space. They're used for a variety of different tasks, including data denoising, image compression, and dimensionality reduction, generally for visualization. Okay, so let's import our libraries. We're going to be implementing this in TensorFlow. So let's import that. We will import NumPy as NP for our mathematical computation. And we will import matplotlib.pyplot as PLT as well. Okay, right. The first thing we're going to do is import the data set. So let's just import data set. And it will be mint data set from tfkeras.datasets MNIST. Okay, and we will set the, I should have dropped down, we will set the X train, the Y train, X test, and the Y test. And we'll set that to minced load data, and that should download it for us. There we go. Okay. What we're going to do now is normalize the values of X train and X test and Y train and Y test as well. So what the normalization does is it'll scale the input variables so they have similar ranges. This helps the model converge faster and basically perform better. So what we're going to do, let's implement that now. So we're going to take X train equals X train as type float 32, and then we're going to divide that by 255. And let's just copy and paste that, and we'll do same to X test. Okay, we'll take that and we'll paste them, and we'll do the same for Y train and Y test. Okay, and what we're doing, the reason we're doing the flow 32 and that, the X train and X test as well as the Y train and Y test, we're basically scaling them from a range of 0 to 255, and that is typical of 8-bit colored images, and that'll bring it down to a scale of range between 0 and 1. And of course, it's often easier for machine learning models to learn data from a smaller range. It also helps with the impact of large input values as well, and that can cause sometimes numerical instability. Okay, so we've done that. The next thing we're going to do, we're going to recast and reshape the X train and the X test. So train. We're going to first reshape. And it's going to be reshaped -1, 28, 28, 1, X image train, TF cast, X image train, float 32. And we'll take that and we will copy it again and change it to test. Test, okay. And the reason we've selected these particular values, we're reshaping them into we're reshaping them into -1, 28, 28, 1. It'll because they will be the tensors being reshaped into a rank 4 tensor with those dimensions. So the value -1 means that the size of this dimension will be pretty much inferred from the size of the tensor and the other and as well as the other dimensions. So if X train has a shape of, say, 60,784, then the shape, it'll be reshaped into 6,028, 28, 1. Okay. And then the cast function, we use that to cast them tensors to float 32 data type. And this we do, this is most often done before performing certain operations, division, and it requires the data to be in a specific type, shall we say. Okay. So let's run that. There we go. So let's just take a look. Print the X train dot shape. Okay, there we have it. So if we then, what we're going to do is use the flatten function to prepare the training data to be compatible with the encoding and decoding layer. So if we go to flatten layer and we set that to TF keras layers dot flatten, and then X train flatten layer X train. Okay, so let's just hit that. I'll put later layer. Let's just hit that again. And what we'll do is print the X train dot shape. And what you can notice is that it's being changed into that there, 60,784. Okay, so we've set up some variables that we're going to use. The next part, we are going to define our parameters that are going to be used by our autoencoder. So learning rate, we'll set that to 0.01. Now all these can be modified yourself. So just have a mess around if you don't want to copy it verbatim. The batch size 256. Display step equals 1. Samples to show equals 10. Global step equals TF variable 0. Okay. And total batch equals int train, and then divided by batch size. Okay, cool. The next thing we're going to do is we're going to set the network parameters. So the first hidden, we will put 256, and that is the first layer's number of features. We'll set that as 128 for the second layer. The encoding layer will set to 32, which is the final encoding that bottlenecks, and then input 784, which is the image data. Okay, cool. So what else could I say about this? The total batch really is just the total number of mini batches in the training data set. And we've calculated that by dividing the size of the training data set by the batch size. The global step, that is a variable that is basically going to keep track of the current training step. And what else have we got? Display step, things like that, the number of the epochs after which the trainer loss and other metrics will be logged. And then the rest are pretty much self-explanatory, the learning rate, the training epoch and whatnot. Okay, so let's run that cell. Right, so what we're going to do now is let's just make a text box and double click create encoder, and this is where we're going to create the encoder. Okay, so let's encoding _1 tf harass layers dot dense, that'll be n hidden 1. The activation function will be sigmoid. Okay, we don't have to put that there actually. Encoding 2, you might as well just copy that like that and change that to 2. Leave the sigmoid activation function, and then encoding final. We will take this part, change this to encoding layer, which we find there, and on this one we'll have the activation value. Okay, and we will then build a encoder function. We'll just call it encoder. I'll take X and we'll put X reshaped, and we'll input the flatten. Oh no, we don't want to put it there like that. We want to set it as a variable, flatten layer X. Encode the first layer, so we'll put layer 1. We'll set that to encoding _1 X reshaped, and then we'll set layer 2, and that will be encoding 2 on X. On layer 1. Okay, and then code, we'll just call that one encoding final layer 2, and what will be returned is code. Okay, so first we've set out our layers there, and we've built up an encoder function. So X is passed into the function. It's passed through the flatten layer, which flattens the input. The flattened tensor is then passed through the first dense layer here with the sigmoid activation. Then the output is passed to the second layer with the sigmoid activation. And then the output of that is passed to the final dense layer with a ReLU activation function to obtain the encoded version of the input tensor. Okay, so let's run that. There we go. Cool. Right. Now we have to, let's make another text block, and we have to create the decoder now. So we're pretty much doing the same thing. So decoding 1, we'll put tf.keras layers.dense in hidden 2 this time. Activation, activation equals tf.nn sigmoid again. Decoding 2, might as well copy and paste that, and then we'll change the hidden layer to hidden layer 1, keep the sigmoid. Okay, and then decoding final equals tf keras dot layers dot dense, and then n input, and then again we will make a build the decoder. Okay, and then you want to call it def decoder, and what it takes in is x layer 1 is decoding 1x layer 2 equals decoding 2, and it takes layer 1, and then decode equals self decoding final, and it takes layer 2, and then what we want to do is return decode. Okay, and input is not defined, isn't it? Have I typed that wrong somewhere? That's why. There we go. So let's hit that again. Hit that again. Hit that again. Okay. So what we've done here, what you'll notice is that layer 1 in the encoder is layer 2 in the decoder, and vice versa. Okay. So the next part then is to construct the model and define a cost function to calculate the lost, and gradient function to calculate the gradients that will be used in back propagation. Okay. So first of all, we'll create a class, and we'll call it Autoencoder. And it'll be tf keras model. Okay. Initialization. Super Autoencoder self initialization. Okay. Self n hidden 1 equals n hidden 1. First layer for the number of features. Okay. Self n hidden 2 equals n hidden 2. Self encoding layer equals encoding layer. If I could spell self, and then self dot n input equals n input of x input, n input. There we go. Right. The next step, we need to now include the flatten layer. So let's just make a space there and put flatten layer equals the tf keras layers dot flatten. Okay. Now we have to put the encodings now. So self encoding 1 equals, we might as well copy this here, because that's what we're doing really. And that one. Encoding 2. Okay. And then we want the encoding final. Might as well just copy all of that, eh? And then just write self like that. Happy days. Okay, and then we'll do the same for the. Might as well just copy that. Put that there. And put self. There we go. That's right, I think. Okay. Now, the next part, we need to, let me just move them over a little bit because they are not aligned, indented correctly. So the next part, we need to define the encoder within this class. Self X, and what we need to basically put in is this part here. And that should be good to go. Encoder. Do the same. X shaped. We don't have to put X shaped there, do we? No. All we have to put there is X. And it has to be self as well, actually. Let's just make them adjustments before I crack on. I was going to do them at the end, but if you're following along, it won't make sense. Okay, that should be X, shouldn't it? Yeah, that's fine. So the decoder, we're going to do the same sort of thing. So just make sure our indentation is correct. And we're going to add self there too. Decoding layer 1, layer 2, right? Okay, and then we have to return code. Okay, there. I'm just my indentations all over the place on this one. Okay, that's fine. Now we're going to define the call self X, and it'll be encoder op self dot encoder X, and just type here reconstructed images, and we're going to put Y thread equals self dot encoder underscore op, and it will return ypred. Okay. Cool. And let's just do 2 more functions. We're going to define the cost function, and it's going to take y true and ypred. And the loss, we're going to put tf losses. It is, isn't it? Losses dot mean squared. I'm going to type supervise for some reason then. Squared error y true ypred. Cost tf reduce mean loss, and we're going to return the cost. Happy days. And let's define the grad. So model inputs targets. Okay, and that will be with TF gradient tape as tape, reconstruction equals model inputs, loss value equals the cost. I'll take the targets and reconstruction. There's a rogue M. And what that is going to return is the loss value tape dot gradient loss value model dot trainable variables, and then reconstruction. Right. Okay. So what this part does, it basically computes the gradients of the loss with respect to the model's trainable variables. It takes the model, the input tensor, and the target tensor. And what it does is computes the reconstruction of the input tensor using the model. It then computes the loss between the target tensor and the reconstructed tensor using the cost function. The gradient of the loss with respect to the model's trainable variables is then computed using the gradient tape context manager and the tape.gradient method. So the gradient tape context manager records the computations performed during the forward pass of the model and enables the computation of the gradients during the backward pass. And then obviously, finally, the function returns the loss value, the gradients, and the reconstruction of the input tensor. Okay, so let's get this trained. So what we're going to do is do model autoencoder. Optimizer will be tf keras dot optimizers dot rms prop, and we'll put in the learning rate will be our learning rate, which we already defined. So for epoch in range training epochs, what we defined earlier, for I in range total batch. I'm not saying it's undefined. Training epoch. Did we call it something else? Epoch, we called it. We just didn't put an S on it. That's fine. So total batch, X input equals X train. What we're going to do here is I plus batch size loss value, grads, reconstruction equals grad model X input, Y input, the optimizer, apply the gradients in a zip, grads model, trainable variables, and then let's display the logs each step. So if epoch display step we need to put print epoch, and how would we want that? It's, isn't it that 040? That should give us a I think anyway. Let's just give it a blast. epoch plus 1 cost equals, we use I think it's that 9F. I always forget these little details. Usually have to copy and paste them from somewhere. Format, and it'll be loss value there. Okay, and I've done that wrong. That should be X. Okay, and then when it's finished, we want to say job done. Okay, so this, what we've written, it trains the autoencoder, and we use the RMS prop optimizer, which stands for the root mean squared propagation. It's basically an extension of gradient descent, and what we've done in this training script, it contains two loops: the outer loop that iterates over the number of epochs, and an inner loop that iterates over the mini batches of the training data set. So for each mini batch of the training set, the grad function is called to compute the loss value and the gradients of the loss with respect to the model's trainable variables. Then the optimizer is used to apply the gradients to the model's trainable variables using the optimizer apply, that should be apply gradients. And after each epoch, the loss value is logged and displayed here. And then job done when we're finished. So let's hit that. What have we got there? We do not have the right prevent. That's why I say I always mess up on them ones. So let's hit that again. No, super object has no attribute autoencoder int. Okay, I think it does though. So let's have a look what we're doing. Model autoencoder. So where are we? What have I done here? I've forgot me underscores. That's the problem. Okay, so let's just rerun this cell and we should be good to go here. Okay, so that's training. I'll pause the video and we'll come back to it. There we go, job done. So, okay, model is trained. Now let's apply the encoder and decoder to the test set. So encode, decode, it'll be model, flatten, layer, X image, test, and it will take that and examples to show. Hit that. Okay, and we can visualize it now. So let's compare the original letters that came into the neural network with the reconstructions. So FA equals PLT, and we will put subplots 210 fig size. Let's just go 10 2. That's a nice size for this. For I in range, examples to show. We need to plot them, so A0, I for them indexes, and then M show NP dot reshape X image test I, and we'll put down 28, 28. Copy and paste that under here, save writing it again, and this time we'll put 1 here. We change that to encode, decode, 28, 28 will be the same. Boom. There we have it. So The reconstructions were quite successful, and you can see that there's some noise has been added to the images. Some aren't as great as others, but that's generally how we put together an autoencoder. Okay, if you've got any questions at all about this code along, any criticisms, comments, questions, and so on and so forth, leave them in the chat on either on the Premiere or leave a comment on the YouTube video. That's it for this week. I'll see you next time.